Hello, everyone. Thanks for joining. This is the fourth session of Protocol Symposium. Today we have Christopher Goes. He is one of the co-founders of Heliax and I guess Anuma project, which is an intent-based blockchain. They have a lot of cool ideas about uh, intents and how we should think about the whole uh, blockchain and blockchain state machines as intent machines and so on and so forth. I know him from his work on IBC and his involvement with Tendermint. And apparently, I just learned this talk is going to be about why all those things were wrong and we have something better to do. So I'm excited to hear about this new work. The floor is yours, Christopher.
Thank you. And thanks to everyone for joining. This looks like an illustrious audience. I'm a bit intimidated. So I'm going to start with like three caveats. The first caveat is that this is the first time I've really tried to give a presentation about this research, which we've really just been like sitting in a room for 2 years with our, not exactly tinfoil hats, but our like I don't know, protocol contrarian hats on, trying to rethink interchain communication and what that even means and what problem we're even trying to solve from the ground up. So this is my attempt to kind of take where we've gone with that research work and repackage it in a format that like actually makes historical sense and connects to existing concepts in, for example, the Ethereum bridging space and stuff like this. And I don't know if this attempt is if this attempt will work or not. So I'm depending on you to give me some feedback there. It looks like this is a relatively small group. So I would say, please interrupt me anytime with questions, with clarifications, with disagreements. I have about 30 slides today. So if it's just a monologue, it won't take the whole hour and we can do questions at the end, but I would far rather that you interrupt me whenever you want. I've adjusted the Zoom window, so I think I can see people if you click the raise hand button, but you can also just unmute yourself and start talking. And please do that whenever you would like. Yeah, the second caveat is that this talk is it's text heavy, and I'm going to try to provide kind of explanations to contextualize things. I would like to have more diagrams, but time keeps moving forward even when I don't want it to. So more diagrams coming next time. Okay, so those caveats aside, this talk is about controllers, and probably, has anyone heard of controllers before? Has anyone already read the paper? You've already read the paper. Really? Wow. Okay. Amazing.
Not the whole thing,
Um,
but they read enough to know what's the control.
right. Okay. So this talk is about a paper we recently published called Controllers. The lead author on that paper is Isaac Sheff, who's a senior distributed systems researcher at Heliax. Not me. I'm just giving the talk. Of course, I worked a little bit on the research, but Isaac's the lead author on the paper. And the kind of subtitle of this talk is Down with Interchain Communication, Long Live State Synchronization. So what do I mean by that? First, let me just kind of give an overview of what I'm going to talk about in what order here to situate things. One, I want to kind of talk about what interchain communication is and some of the problems that I see with it in how we frame that problem today. Two, I'll kind of give a historical overview of what this controllers project that Heliax has been working on is and what its research goals are and why. Three, I'll talk about just the basic sort of system architecture of controllers, the way controllers works. We have a specific way of conceptualizing what's just going on in terms of what the distributed state is and where it lives, what different roles like controllers mean in that context. And then given that architecture, you can try and build protocols that will provide different specific sort of distributed system safety properties. So then in the next section of the talk, Potential Desiderata, I'll talk about what some of those safety properties might be and what the kind of costs are from the protocol perspective in terms of protocol complexity and actual computational efficiency and data storage costs and stuff like this, what some of the costs are. Then we kind of have a proposal for what property we think sort of strikes the most reasonable balance, which is something we call controller DAGs with endorsement. And I will talk about what that is, what properties it provides, and roughly, how a protocol can preserve it. Then I'll kind of come back to the goals and describe, in what way the protocol that we propose here did or did not meet our research goals. Then I will go through some open research directions, stuff we're still working on and would very much welcome collaboration on, and just leave time at the end for questions and any kind of discussions of potential collaborations that people might be interested in. I'm sure there's a lot of open research. Does that make sense? Cool. Okay, so interchain communication today in 5 parts. First, basic abstractions. So if we look at the world of interchain communication today, mostly it seeks to provide, so when you look at some kind of communication protocol or a bridging protocol or the IBC protocol, it seeks to provide an abstraction which allows applications on one chain to send messages to applications on another chain. So by application, I'm speaking a bit high level here, but you might think of an application as a smart contract or a set of smart contracts. In the Ethereum world and the Cosmos world, an application would consist of a module in the Cosmos SDK. In some, I guess Solana world, probably also a smart contract. There are different ways of grouping these slightly, but most general purpose programmable chains have some notion of applications running within them that don't all trust each other, that are in some sense isolated, such as by being different smart contracts. And interchain communication protocols seek to allow those applications to send messages to other applications living on other chains. There are many protocols which have sort of specific differences in exactly what interfaces they provide and exactly how they verify messages, and what sort of ordering guarantees and isolation guarantees and trust assumptions they have, but they're all trying to provide the same send a message sort of API. And that API is, as far as I'm aware, almost exclusively focused on messages, i.e. data, as opposed to code. So it's not focused on sending code from one chain to another to be executed, although perhaps in some cases that's starting to happen. And in particular, it's often focused on token transfers. Now, the kind of way in which these various protocols vary is often in terms of both what their security assumptions are and just what the structure of their security architecture permits. So the kind of more general protocols here, in which the set of which I would include IBC, a kind of recent proposal for something called IBC Lite, which is like IBC, but without so much multiplexing and connections to channels. At least at one point recently, there was something called Gnosis OmniBridge, which runs light clients between Ethereum and Gnosis chain. So that security approach is based on all of the chains involved in the interchain communication running light clients for each other and just using those light clients to verify the messages. Then the other common approach is what I'll call the specific multisig approach. That's taken by, often these ones are called bridges, by bridges like Wormhole, Axelar, et cetera. And there, rather than having everything run like clients of each other, every chain run like clients of every other chain, there's a specific multi-signature account or sometimes a set of validators, which is really just like a rotating dynamic multi-signature account in the case of Axelar, that signs all the messages. And you're trusting them, but given that you trust them, you don't need to run light clients for everything. So what's the hard problem? The hard problem in interchain communication, and the reason why, say, protocols like IBC have to do things like token wrapping, which I'll talk a lot about later, is fault isolation. There are many chains and things that are close enough to chains in this context that we can call them chains like multi-signatures. Some of them will eventually fail in a myriad of ways. They might sign conflicting things. They might go offline. They might sign invalid things. We don't know. But from the perspective, putting on the protocol designer hat, I would argue that we want the safety of user state, including sort of especially assets, to only be dependent on parties, including validator sets that the user has specifically chosen to trust. Even when there are multiple users using an application, such as a token, that might want to make different trust assumptions. If a fault happens, we want impact of that fault to be isolated to users to have specifically chosen to trust whoever committed the fault. And this is important because it preserves like a bunch of incentive alignment. If my assets are exposed to faults related to parties which I didn't choose, then there's not necessarily a reason for those parties to act in a way conducive with preserving the safety of my state because, they don't have to convince me to choose them, right? So this is the basic hard problem. I mean, one way to solve that hard problem, which isn't really solving it, it's just like simplifying it by making one choice is the specific multi-sig approach, which just says, well, all users of our protocol will trust this specific set of parties. And if they don't, the specific set of parties screws up, then the protocol's not safe. But as long as they don't, then it is. That's like the sort of multi-sig bridge approach. The approach of something like IBC is rather to try and build a protocol which can accommodate different choices and somehow isolate faults. Okay, then the typical pattern through which fault isolation is accomplished is some form of wrapped assets. And the basic reason for this is that in order to separate out, in order to isolate faults, you need to track in the state, like where, which parties committing faults might impact the integrity. And the integrity of a token is basically understood as the ability to transfer it back to its source. So the integrity of a wrapped asset here I understand as the ability in the case of like wrapped Bitcoin or wrapped Ethereum, wrapped on some other chain, the ability to transfer that wrapped asset back to the original chain and get the original Bitcoin or Ethereum. So the way that IBC does this is simply to track in the denomination the path of chains that an asset was transferred through. So if I start with Atom on the Cosmos Hub and transfer it to Osmosis, I will get like Cosmos Hub / Atom on Osmosis, where Cosmos Hub is a reference to the light client, the Cosmos Hub. And if I transfer that further to, let's say, Noble, for whatever reason, I would get Cosmos Hub / Osmosis, Osmosis / Cosmos Hub / Atom on Noble. So we're tracking the provenance chain in the asset denomination. And in order to get my original assets back on the original atoms back on the Cosmos Hub, I have to send the asset back in exactly the inverse path that I sent it in the first place. So I have to send it back to, in this case, from Noble to Osmosis and from Osmosis to the Cosmos Hub. Most of these kinds of interoperability protocols and bridges are going to do something like this, even if it's not done in exactly the same way as IBC, because if you want to preserve this information that allows you to isolate faults, you need to track it in the state, which in this case is the assets or tokens. I just want to pause there. Does that kind of context make sense to everybody? Is there some protocol which I've sort of incorrectly characterized here?
Yeah, I have a question. Is that the same pattern as the lock and mint bridges that we see that like you lock some asset on a bridge and it mints you like a wrapped asset on a different chain,
Yes.
and then to go back it burns the wrapped asset.
Exactly. IBC also does lock and mint. It's just a little bit, it's not directly visible to the user, I guess. Like when you tap atoms on the Cosmos Hub, but you send them to Osmosis, your atoms don't get deleted. They just get put in an account on the Cosmos Hub that's tied to, Osmosis, basically an account controlled by the Osmosis chain in a certain sense.
So my understanding is if we start from chain 1 and go to chain n, the wrapped asset thing is going to grow and grow and grow. And besides that, we could have different versions of this wrapped asset. For instance, if we directly wrap from chain 1 to chain n and do the same thing for another unit of the same asset, but go through 1, 2, through 3 through n, we would see both of them as like wrapped assets of type of the same asset, or like is these things going to be fungible on the final chain or not? Generally,
Right. Well, this problem is one of the main motivators for this research, so it's a great question. If you want to do what IBC does and track exact provenance information, you must treat assets that went through different paths as different assets. The reason for this, suppose that we start with the Cosmos Hub, call this A, and then you go from A to B to D, and another person goes from A to C to D. Well, if we treat those as the same asset on D, then the problem is that if B or C fails, now some of the assets can't be sent back to A, and we don't know which ones they are, right? So now we've like lost some of the provenance information, which means that we lose the guarantee we were trying to provide. A user who chose to trust B and not C might in fact be affected, unless we remember in the asset denomination which specific path each asset
Makes
took.
sense. Makes sense.
And that, I mean, of course, the fact that these tokens are not fungible is kind of a huge annoyance. Like, it's annoying for users. Most of the time, these chains or parties aren't actually committing safety violations, and then we have to introduce, all these intermediate, I don't know, stable swap pools and like all this other stuff. It's annoying. And it's, as a user, I want to get my assets back, I have to go through this long sequence of transfers. Now there are some limitations to like, there's a sort of theoretical limitation here, in that if we want to preserve this fault isolation, we must preserve this information somehow. But then there are, I'll get later into the presentation into at least some things that we've managed to do that help alleviate some of these problems. Cool. So as you touched upon already, a few kind of limitations of this paradigm from my perspective. One is that really the bridging is focused on data, not code. Two, there's no privacy. Or not only is there no privacy, but typically the way that fault isolation is maintained is not compatible with privacy. Like, even if you had shielded pools on two different chains, the way IBC works, in order to track assets sent between all of these chains, we need to just add the like balances together when we're minting and burning. That's the way most mint and burn bridges work as well, to prevent more wrapped assets from coming back than were originally sent. So that requires the ability to have the amounts of clear text, you can add them. So that kind of fault isolation is not compatible with privacy. Another limitation, unwrapping assets, as you mentioned, requires a bunch of user interaction. It's time consuming. And also, it's just not like, from a computational efficiency standpoint, it's kind of not super efficient. Like, you have all this action going on from A to B to C to D to E. And now in order to get back to A, you have to send like 6 transactions or something. It just seems like maybe there's something better we could do to at least batch and amortize some of these things. The final limitation from my perspective is the developers have to write a bunch of chain.send calls. And you might wonder, what could we do instead? Well, that was the question that we asked ourselves about 2 years ago, when we started on this so-called controllers project. We had 5 goals. The first is to provide to design an interoperability system that would provide a high level of abstraction for developers, so they don't have to call like explicit send message all of the time. A protocol that's capable of bridging both data and code. We wanted to cleanly separate application logic from state provenance information. We wanted the ability to automatically simplify the provenance graph. By the provenance graph, I mean like A to B to C to D to E. A to B to C to D is the provenance graph, right? The graph of what sort of historical things have happened in the history of a particular piece of state, or later I'll use the word resource, that we need to track in order to provide this kind of fault isolation. And finally, we wanted a protocol where fault isolation, at least in principle, does not require compromise of privacy. This is a separate decision, I want to note, from whether or not to do private bridging. I'm not saying like all bridging should be private, or making a protocol that only supports private bridging or something like this. We just wanted a protocol that was in principle compatible with it, such that that choice could be up to users and applications. So just to kind of bound the possibility space for what we can do when we think about interoperability protocols, if you zoom out and look at like, there are many pieces of state living on different chains. And there are, in my view, there are kind of 3 fundamental services that are happening on those chains most of the time. Data storage, computation, and ordering. And those services, from the perspective of interoperability, are quite different in that data and compute can happen in many places, or storage and compute can happen in many places. I can store a piece of data in lots of places that doesn't cause any interoperability problems. I can do computations in lots of places that doesn't cause any interoperability problems, especially when I could just always verify computations with succinct zero-knowledge proofs or something like this. But regardless of what kind of fancy proof techniques you have, a particular piece of state must have a canonical ordering location. For a particular piece of state, there must be one and only one place. And later I'll use the word controller to refer to this place, but you can also think of just a blockchain where changes to that piece of state can be ordered. Otherwise, two different observers might not agree. If there's more than one place where a particular piece of state could be ordered, then one place could make one ordering decision, another place could make another ordering decision, and two observers could see two different orders. This is true even if everyone is honest, right? It's not. So each piece of state must have a canonical ordering location. So that's actually kind of just where we start. Like, let's not make any more assumptions than necessary. So we take that kind of basic bound on what's possible and define the notion of a controller. And the controller of a piece of state is simply who must order and authorize any changes to that state, and who is just some process or set of processes that can produce, let's say, a signature or a generalized signature, like a light client proof, that we can verify elsewhere. And that controller must be able to order and sign over a total order on all of the transactions that it processes. So you could think of a controller as roughly a blockchain without necessarily the compute and storage parts. Let me also stop there and ask, does this make sense? Getting ambiguous responses.
But my understanding is controller in this abstraction is just the entity who has the right to sequence state updates or state transition or transactions or something like that. And
That's right.
Yeah.
So I mean, the way that we enforce this in the protocol is just that when we check, when we validate whether a state up to see what we think the state is, given a particular piece of state, somehow in that piece of state, we reference who is supposed to be able to order updates to that state, and that's the controller. So, implicitly, say Ethereum state has the Ethereum main chain as its controller. The difference with our research is that we kind of make that more explicit, but it's already happening.
Cool. Right. I guess a good example for to illuminate what the controller is in the context of a sovereign rollup. The controller is exactly the sequencer, and it doesn't have to have execution and other things either. And doesn't have to be the place that we store the data either.
Right. The controller is defined not by the protocol used to create signatures, but by the protocol used to verify state changes. So defined by the client. So if I am a client of a sovereign rollup and I use the signatures by the sequencer, as I understand your example, to determine the canonical order, then that sequencer is the controller, yes. I mean, you can have controllers that are created as more complex hybrid functions of, I don't know, check the DA layer's order and the sequencer's order and use this function to combine them. That's fine. That's just an abstraction. Cool. So the other thing we try to do with this controllers notion and how we think about the system is to reframe the problem as one not really of message passing, but rather of state synchronization, as in from the perspective of a user, an application is defined more by the set of abstractions it consists of and how changes to that state can be processed than by a particular chain. So rather than living on a particular chain, we think of applications as having state that lives on many chains, and what users and developers want, rather than explicitly sending messages from one part of an application on one chain to another part of an application on another chain, they simply want the state to be synchronized and to be able to get state from one location to another location when they need to get it there in order to do something from the perspective of the application. Cool. Just being slightly conscious of time, let me go briefly into the system architecture. So I want to describe 4 kind of concepts here: controllers, resources, transactions, and controller labels. Most of these should be pretty straightforward, so I'll go quickly. A controller, as mentioned before, a controller is the party who orders. Controllers do not necessarily store state or perform computations. The other notions that are useful to have here are those of safe controllers and live controllers. Safe controllers are controllers who do not fork, namely they commit only a totally ordered sequence of transactions. And live controllers are controllers who eventually process transactions. These are the safety and liveness properties of consensus algorithms that you're already familiar with. Resources, we have this system in a nomen based on atomic units of state called resources. However, this is at least, it's not tightly coupled to the controller's design. So you could have some other system that wasn't exactly like resources and still use this kind of controller's design for interoperability, which is why I'm going to kind of align the details here. There's another paper on our research topics archive called The Resource Machine, which you can read if you're interested. But for the purposes of this presentation, you could think of resources as like generalized UTXOs, or I think Cardano has something called EUTXO, which is quite similar, or Zexi records, whichever of those you're most familiar with. So a controller is a piece of state that contains both, like at least references to some data and a reference to a function which governs how that state can change, which we call the resource logic. So in that sense, it's also like a smart contract. There are a bunch of specific differences, but I'll refer you to the paper there. But like smallest atomic unit of state is a resource. A specific resource, a given resource can only be created and consumed exactly once. Yes, transactions are atomic state transitions as usual. And in the model of resources, transactions include sets of consumed resources and sets of created resources. Now, in particular, in this context of controllers, transactions can only update state controlled by one controller. So only, specifically, only all of the consumed resources in the set must be controlled by this controller. This is already, true when you send a transaction to Ethereum. It's only updating Ethereum state. We've just made this controller abstraction more explicit. However, input resources may have been created on another controller. Now they're only being consumed on this controller, and I'll get into the details of that in the next section. So controller labels. Somehow we need to take this provenance information and encode it in our atomic units of state resources. And we just call this like field, which encodes it, the controller label. Resources carry these controller labels, which encode broadly which controllers have affected the history of their resource. So this is like if we go back to the example of IBC and wrapped assets A to B to C to D to E, the A to B to C to D to E part is like the controller label. We just generalize it. It can be generalized in a few different ways later at DAG, but at the very least, these labels must include a creating controller who signed off on the creation of the resource, terminal controller, which is where any consumption of the resource must be ordered, and often they will include affecting controllers who've influenced the resource's history. Any questions here?
I can ask a quick question. Could you give us a toy example that makes it explicit or clear why having this resource abstraction is useful? Is it useful because we can lock parts of the state, or is there any simple example that shows that?
Well, I have this diagram in the next slide, and maybe it's helpful. I mean, if your question is why do you need resources as opposed to smart contracts, the main difference is that we want to package data and code together in the sort of smallest bundles possible. So if you compare an ERC20 token on Ethereum, an ERC20 token has a single function, the smart contract code, which governs how the state can be updated, but it has a bunch of individual balances. And those balances, at least conceptually, can be changed without necessarily needing to worry about all of the other balances. Like when you're transferring a token from one party to another, you just need to conserve tokens, and you need the transfer to be authorized by the sender. And we want to, in our model, for various reasons, including the ability to execute transactions concurrently and the ability to execute shielded transactions, we want to separate out state and code into these minimal bundles, which we call resources. You could, I think you could use controllers with smart contracts as well. Like you could have many pieces of state governed by one function. I think that would work. It would just require a little bit of rework of some interfaces, but nothing fundamental should change. To give a specific graphical example, imagine that you want to make a salad and you have, I don't know, a few ingredients for the salad: tomatoes, cucumbers. In that thing, there's supposed to be watermelon, but I don't know where the watermelon went. And we have 4 different controllers, A, B, C, and D. You start out with a tomato and a cucumber on A, send the tomato to B, send the cucumber to C. Some other stuff happens here, which I'm going to skip. Produce a salad on D, and eventually you send the salad back to A. And what we want, and part of what we want to accomplish in our protocol here, is the ability to send the salad back to A and remove all of this history without sending all of the individual components back through B and C, if that makes sense. So in the IBC sort of wrapped assets world, I mean, one, you can't really do this at all because you have to deal, just with assets. But if you start off with tomatoes and cucumbers and send them all the way to D, there's no way to and send the salad back to A. You would just have all of this history, and it's not clear how you would. There's no way, at least with these kinds of graph assets, to remove this history from those from the salad without sending the individual components back to A and trying to just make the salad on A directly, right? So it's this kind of simplification that we want to be able to provide. So in this architecture, we have kind of a few options as to what actual sort of distributed system safety properties we want this protocol to maintain. We've identified at least 3. One of them, the weakest one, is causal resource history. Causal resource history is simply the property that any resource with causal resource history was created in a valid transaction whose inputs were resources that also had causal resource history. This is the weakest property because this is like the equivalent of a recursive ZK-like client or recursive ZK, I guess recursive ZK full node validity checks all of the history. And in particular, it still permits histories, including double spends, double consumes. But that's checkable with just recursive proofs. Serializable resource history, sort of the strongest property of these 3. Serializable history, resource history is the property that each resource reflects some fully serializable history featuring only correct atomic transactions and no forks or double consumes. This is possible to maintain for every resource, but it's very expensive. And there's kind of proof and description of that in Appendix A of the paper. The third property, which is the one that we'll focus on in the next section, we call consistent controller labels. Consistent controller labels is the property that if a specific resource does not have serializable resource history, then it has an unsafe controller and the affecting controllers, which are part of the controller label. And if, in fact, a resource's affecting controllers are safe, then the resource, in fact, has serializable resource history. So this probably sounds a bit obtuse, but it is actually the generalized version of what something like wrapped assets and IBC do. So in wrapped assets and IBC, if you send A to B to C to D to E, if you just look at the asset on E, you don't actually know that you can send it back to A because there might have been forks. Now, if all of A to B to C if all of A, B, C, and D were safe, then in fact it should be the case that you could send the asset back to A. And this is the second part of this statement here. If in fact the resources affecting controllers are safe, then the resource in fact has SRH. Does this make sense?
It does.
Cool. Right. So our proposal is that this is probably the kind of property that strikes the best balance, at least for now. And we kind of build 2 specific protocol mechanisms to preserve this, controller DAGs and endorsements. So the basic approach is to maintain a DAG, directed acyclic graph, of affecting controllers in each resources label. And to have a mechanism for endorsements, which allows removing unnecessary controllers from the affected controllers. So basically removing unnecessary parts of the DAG as soon as we can confirm that the state changes which happened there are consistent and that no one else, like in the DAG or in parts of the DAG which we care about, will endorse conflicting histories in the future. So each controller must maintain some state in order to do this. And I'm kind of, This protocol is still a bit complicated. It's actually more complicated than we would like, and we're working to simplify perhaps a few things that could be simplified. So I'm sort of giving a mid-level of detail here and lighting over some stuff that you could find in the paper. But each controller must store basically three things in addition to the resources or resource commitments and nullifiers. They must store specifically for the purposes of this kind of controller interoperability an endorsement map, which is really what you're already familiar with the sort of multi-light clients of IBC or other light client bridges. An endorsement map is a map from controller ID to state roots of that controller that we verified, and these endorsements can be updated with light client proofs and a proof in particular that the controller being endorsed. So if I am A and I'm updating my endorsement of B, I need a proof that B has not endorsed a fork of me. That would, of course, be inconsistent. This is not a proof that IBC provides, for example. So there is a slight distinction here. And each controller tracks a set of resource, we call them sends or send records. Send records fundamentally represent promises. So when a controller A transfers a resource to controller B, we want somehow for A to track that it has done that so that A can promise to accept that resource, or so to speak, back in the future or something descended from it. And we track that promise, and that's a resource send record. And a set of resource receives, which tracks information about resources received from other controllers. So each resource's label in this model includes this kind of DAG of affecting controllers, and it includes a creating controller and a terminal controller, as I discussed earlier, and some more metadata, which is not integral to understanding this part. In order to transfer a resource on the sending controller, you create a new sent record, you create the sent resource, which then somehow gets synchronized on the receiving controller, later happening sort of asynchronously later than what happens on the sending controller, because you must verify what happened on the sending controller. You endorse a new state root from the sending controller, which then commits to the resource in the send record, and you create a receive record corresponding to the send record. And at this point, this is sufficient for then later a user to send a transaction that consumes the resource on the receiving controller, if this makes sense. So we kind of separate out, at least possibly, we separate out these two aspects of the state change. And this can be batched. So it could be like we do a bunch of send record creation on the sending controller and then relay a big proof to the receiving controller. Then we've got all these receive records, and then like users can do things. So from the perspective of a wallet, or something that's showing users what their assets are, as soon as this has happened, really the resource is on the receiving controller, even if it hasn't been consumed yet, because the receiving controller has the ability to process a transaction which consumes it. So the critical operation here is endorsement. And the basic idea behind endorsement is that if a resource history involves moving to an intermediate controller, doing some transactions and moving on, the intermediate controller is arbitrary and can be removed once a bunch of conditions are checked. And to go back to my graphical example here the intermediate controllers are B, C, and even eventually D. When I transfer the salad back from D to A, the controllers B and C and D were involved in the history of the production of the salad, but as soon as I verify a bunch of things, I should be able to remove them from the history. And what I need to do in order to verify those things is basically constructed in order to guarantee that as soon as I remove certain controllers from a controller DAG, I know for sure that none of the other controllers still in the DAG, if there were some ancestor controller in this case before A, will accept any other history other than one consistent with the controllers that I have just removed. Basically, I make a bunch of proofs that say that, oh, my ancestor controller has processed state roots of all of these intermediate controllers after these specific state transitions happened, and it will never accept any earlier forks or something like this. So I then can guarantee that I don't need to track this provenance information anymore, because the ancestors controllers who I want to potentially be able to send the resource back to in the future won't accept any histories of some other thing happening in between. Does that make sense?
Like if you go back to the salads diagram,
Yeah.
what you just described means A will not accept either 11 or 9, or like, is that true? Or for instance, like
Let's see.
this gray line here seems to be doing something inconsistent.
Right. So the red line is a potential fork of controller B. And what this diagram, slightly confusingly, is describing multiple possible histories. But what the operation of endorsement guarantees in this case, suppose that A, and we see this history where, say, A sent tomato to B, B sent it to D, and D used the tomato along with a cucumber to produce a salad and sent it back to A. If A endorses, when A endorses the histories, this history specifically of B sending the tomato to D and C sending the cucumber to D, then A, by virtue of that endorsement and some of the other protocol logic, guarantees that A will not accept this transfer of the tomato in some conflicting history. And this guarantee is what allows us to basically turn this chain of promises back to a more simple form. And in particular, the thing here, which is different, quite different than something like IBC, is that this sort of removing intermediate nodes from the controller DAG, at least sometimes can be done kind of automatically, like without explicit interaction from the user. It still requires sending transactions and tracking things, but it doesn't require the same thing that IBC requires, which is that the user literally sends the asset, all the way from E back to D, C, B, and A. Okay, so this protocol specifically does not guarantee serializable resource history because some of the controllers could have forked. But if you want to verify serializable resource history, you can do the same thing that you would do in something like IBC and get a bunch of state roots from the affecting controllers of a particular resource and check that they've endorsed things consistent with check that they've endorsed things consistent with the history that the resource itself tracks. Okay, maybe I'll just go through the properties to go back to our design goals and then open the floor to some more questions. So originally we set out to design a protocol which would kind of have 5 properties, a higher level of abstraction, no explicit chain.send. I think controllers accomplishes this. There are resource transfers involved, but this is at the level of like the application. Like if you think of sending an asset, to send an asset on Ethereum, you send a transaction, and here there's just not really any distinction anymore between sending an asset to another account on Ethereum and sending an asset to another account somewhere else. Both require a transaction, but developers don't need to write like extra logic to handle cross-chain sends. Capable of bridging both data and code, yes, although to some extent this depends on like the specifics of the resource model, state architecture, and some standardization of how you interpret code. Cleanly separate application logic from provenance information. Yes, I think it accomplishes that. Automatic simplification where possible, yes. Fault isolation does not require compromising privacy. At a high level, we think that this approach is compatible with that in the sense that we've like enumerated all of the proofs which must be made, and it doesn't require the kind of balance tracking that IBC does. The individual like checks for different resources are sort of isolated from each other. Still, though, in order to track these send and receive records, you need to track some information, and there is a bit of a trade-off between automatic simplification of the provenance graph and privacy. Because if you want to do automatic simplification without explicit user interaction, someone needs to have the information necessary to create the proofs to allow for the controller DAG to be simplified. And that at least is some metadata, even if it is not directly the data that the user would want to keep private. So there's some intricate trade-off space here that we haven't fully figured out. But that trade-off space is mostly like I don't think we've proved that it's kind of always going to be a trade-off axis, but at least there are probably some restrictions in principle there. Yeah, we've just recently released this controllers paper, but we have a bunch of future work already planned. We want to simplify things. I aligned over a lot of details, particularly in how endorsements are processed. And although I don't know if it's more or less complex than IBC, I think it's simpler in some ways and more complex in others, but we would like to try and simplify things further. This is still at the level of like a protocol, architecture and abstractions. And we want to figure out a bunch of efficiency improvements to batch stuff, maybe simplify some of these records. We want to describe a full shielded protocol and investigate other techniques for preserving SRH, which we haven't proved is fundamentally expensive. We just haven't yet found a way to do it that isn't too expensive. So maybe there is a way. And we would like to investigate also the question of liveness. Most of controllers deals only with safety, which is easier because you don't need to reason about who is providing data availability or who will respond to queries when you request certain data, which is needed to make proofs to actually do things. So the question of liveness is one that we want to investigate as well. Yeah, that's about it for this presentation. This was kind of just a pitch for the paper, so I'd encourage anyone who found this interesting or even just, I don't know, weird enough to warrant investigation to take a look at the paper, which is probably clearer on some of these explanations than I was. I'm also, that's my email in case anyone wants to contact me, and I want to open the floor here to other questions or potential interested collaborators.
I have a question. Thanks for the presentation.
Yeah.
It sounds very interesting, but I'm having a hard time to kind of visualize how this would work in more concrete terms in practice. So for instance, you talked about the simple example of token transfer. And in the controller model, there was the send record and receive record, I believe, which sounds very similar to me to message passing. Like if you want to implement token transfers on this model, how would that work? What would be the controllers and what would be kind of the flow of the whole interaction?
Right. I mean, in some sense, the send record corresponds to something like when you have a mint burn bridge, when you or a lock, whatever you called it. Sorry, I forgot. Lock and mint bridge. When you have an asset on chain A and you lock that asset in order to bridge it, the locked asset it's not exactly the same as the send record, but it's a little bit like it. It's a way of tracking the promise that chain A will accept this asset back in the future from chain B. The difference here is that we're implementing this, sort of at the level of the state architecture, so it can be done for all resources in a standardized way, rather than being something that you like write different kinds of, bridging protocols for, if that makes sense. So in the case of a simple token transfer, which you asked about, it would indeed be similar. If I'm just transferring a token from A to B, I consume the token resource on A, I create a new resource, which is configured so that only B, the terminal controller, can consume it. I create a send record on A, controller B endorses A, so there's some kind of light client proof that goes from A to B, perhaps relayed by a third party or node operator. Chain B checks the send record, creates a receive record, and then the resource can now be consumed on chain B.
Okay, got it. So this sounds kind of like a generalization of the message passing architecture. But what I'm kind of confused about is you mentioned distributed state. So I thought for a token that exists in some form in chain A, B, and C, there would be a single controller that manages all the state. But in your previous example, it sounds more like that chain A is one controller and chain B is another controller.
That's right. Yeah. When I talk about distributed state, I'm talking about distributed state from the perspective of an application. So if I am thinking about things from the perspective of a token application, like let's call it the token, the USDC token, that's a clear one. As a user, I think about USDC as one application. And I could have USDC tokens on many different chains. I could have them on Ethereum. I could have them on Noble, on Cosmos. I could have them on Solana. But I think of those, I think of different USDT tokens on different chains as, still part of the same part of the state of the same application, just with slightly different trust assumptions. That's the kind of distributed state that I'm talking about. I mean, I think, of course, there's still message passing happening in this protocol. It's just not something that a developer would explicitly need to write, as opposed to like in the current system, if you are writing a token contract or something like this, maybe you deploy your contract to multiple places and people can make wrapped assets or something like this. But some explicit action needs to happen on the part of the developer or someone connecting to the system to enable interoperability. And here, rather than create code that sends messages around to enable interoperability, developers would, if anything, only write code to restrict what kinds of interoperability can happen in the resource logics, let's say.
So in the USDC, in the USDC example, my understanding is each of these resources is like a kind of look like a UTXO for the USDC, and it carries its own smart contract logic around. And if this like maybe I have 10 USDC, I send it to a chain that its controller has never heard of like USDC or anything like that. But because the resource is carrying its own code and logic, it can be transferred to other places.
That's right. Now, the one note I would add there is by carrying, we mean carrying an immutable reference, i.e. a hash that refers to a resource logic, not literally storing the code, which would be too expensive to duplicate.
Makes sense, yeah. I have a question about like your comparison to like a smart contract calls and doing a transaction on a single blockchain. Like you mentioned that in this model, when you send resources around, it's like sending resources around in the same blockchain. But I feel like I'm not sure if it's like a good frame of thinking about things or not, but I feel like we kind of lose atomicity in the sense that is it the case that I can have a transaction that takes a resource to a new controller and does something to it, and in the same transaction transfer it to another controller? Because like in a unified like controller or a unified blockchain, I could do that, but in this design, it feels like shouldn't be able to do that.
Right. So, I mean, there's always still going to be the restriction, sort of, which I mentioned somewhere. I mentioned here that a single transaction, an atomic state transition, can only alter state controlled by one controller. So if you want so-called synchronous atomic composability, you must have all the state that you want to synchronously atomically compose be controlled by one controller, at least for the duration of the transaction in which you want to synchronously atomically compose it. That's just how distributed systems work. No interoperability protocol is going to be able to get rid of that limitation. What I meant by it being the same is like, so when you send an asset on Ethereum, at least implicitly, you transfer a token, you consume a token that's currently in your account and you create a token that can now be spent by somebody else. And implicitly, you're creating that token that can now be spent by somebody else on the Ethereum chain, right? Like that's the promise that's being made by virtue of processing that transaction. The Ethereum validators promise, at least implicitly, to accept some future transaction if I sent you a token in which you can send the token to somebody else. And the part here that's generalized is that instead of that promise being made just implicitly by the Ethereum validators, you can also say, I transfer tokens to you and you are going to be able to consume these tokens on another controller. Now, some bookkeeping logic has to happen here that I talked about with these send records in order to make that possible. But from the perspective of the user, it's like kind of the same experience. And from the perspective of a developer, no additional effort is necessary.
Makes sense. I really like the abstraction, and I'm very confident that this can like like make things that were not so visible to us more visible to us, like in terms of figuring out new protocols. So thanks for the presentation. It was great.
Thank you.
In terms of like, I think we can pause the recording that we publish on YouTube here.